Okay, then hello everyone, and thank you for joining this call and welcome back. Today, Professor Steffen Staab will give a talk on knowledge graphs and semantic web. Professor Staab holds a Cyberwall Endowed Chair for Analytic Computing here at the University of Stuttgart in Germany, and also a chair for Web and Computer Science at the University of Southampton in UK. He has authored and co-authored around 16 books on knowledge graphs and semantic web and ontologies, and hundreds of papers, as far as I know. So thank you very much, Professor, for giving this talk, and thank you for joining us. In this call, as much as I see, beside workshop participants, we have also some researchers that I met at the Linked Building Data summer school. Happy to see you here. And then we have also Daniel. Dr. Daniel Hernandez is Professor Staab's postdoc, and he's working with open data, databases, and the semantic web. Just after this talk, he will give a tutorial on GraphDB and Sparkle queries. And yep, thank you all for joining us. If you have questions, please use this opportunity to understand better knowledge graphs and the power of semantic web. Professor Staab, the floor is yours.
Thank you very much, Elsa, for this nice introduction. So I'll open the chat. So feel free to interrupt during my talk. Elsa asked me to give a more introductory talk about knowledge graphs and the semantic web. Now, when I hear who's participating in the workshop, I hope that's not too elementary for you. Anyway, if you feel like you have not understood something, or you don't care that much about the specific slide, but you would like to know something else related to what I present, please interrupt. And I think we are not such a huge round, so we can have a bit of a dialogue about what I plan to present. So expectation here is I want to give a little bit of an overview of what knowledge graphs and semantic web are about. So let me see what I can move this away. No. Okay. So what is a knowledge graph in the first place? It's a graph. So as a computer scientist, we define a graph by describing a set of nodes, vertices, V, and a set of edges that connects these nodes. And here below, you'll find an example from our knowledge graph book. At the end, I give you a link for that because you also can interact with the book online for free. You can also buy it. I don't get any reimbursements from that, so feel free to just use it online. And what it shows here are objects, which is what we represent in these graphs, namely each node or vertex represents entities or objects or values and classes. And here we represent an object like EID 15. So this is just an abstract identity. And it is of a certain it belongs to a certain type, namely an open market and a food festival and a drinks festival. And there is another EID 16, which also is an open market and a food festival. Both are placed at different venues, like at Sotomayor, which is in the city of Vina del Mar, or at Santa Lucia, which is in the city of Santiago. And there are connections between them. So what you see here with these nodes, that they stand for objects, and then the relationships describe how these objects are related to generalizations, namely classes, like a food festival. And some of the other links describe how, for example, two cities are connected, namely you can go from Santiago via bus to Vina del Mar. These connections are directed, and here, if they go in both directions, we have also an edge going in both directions. And you can have multiple edges. It is crucial that these edges are labeled with annotations like bus. And here it is expressed that there is not only a bus connection, but also a flight connection between these two cities. So what we get when we look at these graphs are, on the one side, facts, like a specific object is a kind of a food festival being in some place. So these are facts. What we get is terminological knowledge. We learn, even if that is not completely visible here, what a food festival is, what a drinks festival is, what an open market is. And this is terminological knowledge which applies not to a specific object, but to a class of objects. And what is core to knowledge graphs as they're in use now is that they aim at large scales. So some of the larger knowledge graphs, they go beyond 10 to the power 9 many facts, so more than 1 billion facts is what you encounter now in the bigger of these knowledge graphs. And the graphs are there in order to represent this knowledge that I talked about. And of course, one could ask, now what's different than what people did 10, 20, 30 years ago? And the way to think about it is by looking at what would be the competitors for representing such kind of knowledge. And people have explored them. I mean, relational databases are probably the most used representation for storing data. And they provide us with very nice capabilities. Relational databases are very mature. But what they do not have is the flexibility that we need when we have rather open world knowledge. What is typical for relational databases is that they structure the objects in tables and that they work very well when these tables are well filled. But what if about some objects we have very little knowledge, about other objects we have a lot of knowledge? This is very typical for facts. We know maybe a lot about the city of New York, but maybe you may already know less about the city of Stuttgart, where I'm in, and you may know even less about the village of Zellingen, where I was raised. It only has 3,000 inhabitants, so probably no one of you knows it, and you only know now that it exists. So the knowledge about certain individuals is spread very unevenly. And when we want to represent this with great flexibility, and when we also want to represent terminological knowledge, then relational databases do not offer a good fit. Another alternative, which has been explored for a long time, is logics. So actually, since the 70s, first starting with Prolog, then going on with description logic since 78, people have explored how to store terminological knowledge and factual knowledge in logics. And that works very well, but it has issues with scalability. It also has issues with offering a kind of an interface that people can understand very well. Nevertheless, logics plays a major role when we talk about knowledge graphs, just as also relational databases still play a major role when we talk about knowledge graphs. Then there are other representation mechanisms like document databases and so on and so forth, but the graphs are very general in that they allow to represent almost anything that you find in these other paradigms. They're not as expressive as logics, for example, but that they work as a kind of a least common denominator for representing knowledge. So it's not so difficult to map a relational database onto a graph database. It's not so difficult to map a document database onto a graph database. And even a good part of the logic representations can be mapped onto a graph database, not everything. So we have this common denominator, which is really great to have. So now, in order to give you an overview of knowledge graphs, I want to point back to a paper which appeared in the communication of the ACM and at this magazine Q, which resulted from a panel at the Semantic Web Conference 2018, where several companies, Google, Microsoft, IBM, Facebook, and eBay, were asked to describe the state of play of large knowledge graphs in their in their companies. I pick a few of them. Yeah, I mean, there are many other companies, and actually also I will show you like 2 other companies and what they plan to do. So what is the overarching challenge that all of these 5 mentioned companies use knowledge graphs for? It's basically access to information. Access to information when the information representation needs to be very flexible. So let's look at these examples. I'm not sure what's happening now. So for example, Microsoft is not just one company. In a way, it's several companies. It's Bing, the search engine, where for Bing, Microsoft needs information about people, because what do we search for? We search for people, we search for places or organizations, things, actions. And these kind of entities, objects, they need to be related. Microsoft Academic used to have the academic graph. Unfortunately, that has been abandoned by now, but also there it was about people, publications, fields of studies, venues, and so on and so forth. Of course, Microsoft has infrastructures like Office and Teams, where there is a kind of a work graph. And again, it's about people and groups. The people communicate using messages. They have certain activities or projects. Again, we can represent objects and how they are connected. And finally, LinkedIn is a knowledge graph, because there you have people who advertise their capabilities. There are job announcements. There are universities and companies. And when you look at these different worlds, as diverse as they are, searching information on the World Wide Web, organizing scientific research, having collaboration in your office, working or like exhibiting job profiles to the world, what do you find? You find overlap. And you might want to bring these different bits and pieces together in order to ask complex questions. Yeah, you might be interested to ask which colleague of mine has published a paper about knowledge graphs and has worked before for a company in the architectural domain. Yeah, that would be an interesting question to ask. University of Stuttgart has 5,000 colleagues. Maybe some did exactly that. Actually, it was only like 2 weeks ago, I was attending a meeting and I learned yet about another person who works with semantic web technologies. And I've never expected there in an institute, which I don't even remember the title, which was very far away from computer science. And so it's not so easy to find this information, who works in this, in a company, in my own company, using certain technology. It's basically impossible to find. And it might well be stated in this combination of the work graph, the LinkedIn graph, and the academic graph. And that's what knowledge integration using knowledge graphs is about. There are inherent challenges in all knowledge graphs. And so I restate here what Microsoft said. It basically applies to all the other knowledge graphs too. So in which way do you want to scale? Well, one way you want to scale is, of course, coverage. You want to have as many facts as possible. The other way you want to scale is you want to have facts which are fresh, which are up to date. Yeah, if I ask about who's the president of the US, and I give you an answer like Barack Obama or Donald Trump, I guess you wouldn't be very satisfied. Yeah, though of course these two men are still titled president, they're obviously not the acting president of the United States. We need fresh information. Now, okay, and president is updated every 4 or 8 years if it's president of the United States, but other things change daily. What if you are interested in a flight information? Yeah, the flight information might be updated per minute. Yeah, how much is the delay of a certain flight? Or what are the average delays that flights have? So these things need live information from an information source. And you may want to connect this live information together with older information, more mature information. And finally, having information is good, but of course you want to have correct information. Yeah, I mean, if you asked Donald Trump about who's the president of the United States, he would say it's Donald Trump probably. Yeah, claiming that he was elected wrongly. I think we probably would all agree. So it depends, of course, whom you ask, that you also want to have correct information. So this is now this triplet: coverage, having many facts; freshness, having up-to-date facts; and facts should also be correct. And it's very difficult to ensure this triplet all at the same time. This is also true when you look into application domains like architecture and construction, because also there you have different states of the world described at the different contractors. These contractors will have information in their information systems, which for their own work might be the freshest information. But the other partner might not be able to see this information directly, which makes it maybe difficult to coordinate the working. Okay, so this is a problem. And then of course, the problem that we have also is about identity. Identity actually in knowledge graphs is a huge problem. Here it's illustrated with Will Smith. So if you ask for Will Smith, who is it? I actually knew only the first one, famous actor Will Smith, but it seems there was also a famous baseball player, Will Smith. I have no idea about baseball. And there's also like a footballer, Will Smith. There is also some other celebrities, a comedian and someone else, Will Smith. And these are just like the famous Will Smith. And the question is, when you ask for Will Smith, whom do you get? Again, in a construction domain, you may run into a similar problem. Yeah, you may want to ask about a certain portal entry, but there may be two portal entries. You may ask for a particular construction element, and of course, it's very important that you get exactly the right element. This may sound trivial. In practice, it is always, always, always very hard. Here is an example about identity from eBay. I mean, eBay does a nice job offering a knowledge graph view on their products. So what you find here is a long list of things, attributes that, that allow you to select certain kind of products. For example, here, when you search for a thermostat, then you may indicate the brand. So it recognizes that Nest actually is a brand, but of course you might switch to other brands. Actually, this thermostat has other kind of attributes. For example, smart home compatibility. There are different kind of kits that allow you to integrate such a thermostat, right? And there may be ones from Amazon, from Apple, from Google, from Logitech, and so on and so forth. And of course, when you buy one and you have a certain platform at home, you are interested to find the one that fits. So this is not only about the item itself, it's also how it fits into a certain environment. And this needs to be modeled. And this is a challenge because when you look, when you search for thermostats and then you look at individual offers, remember eBay is not like one centralized seller. It's rather a platform for sellers. These are the things that you get. Yeah, and typically what I do is I might look for the cheapest product, and then what I get is not the thermostat, but I get a covering for the thermostat or something awkward, yeah? And that happens very often. And of course, you need to understand that even though the covering of a Nest thermostat is maybe a very cheap product, it's not really what I've been asking for. So now we look at these results. We see all kind of Nest and other thermostats. The question even then is, if I have this one here and this one there, are these the same thermostats? Now, when we think of electronic products, it is very challenging to identify when two products are the same. They may be the same and just have a different price. It could also be that one of the two thermostats has a longer, has more memory and a longer history that you can query for. So when something becomes the same, has the same identity or not, is a very challenging question. Here is another example from Google. Google also gets its fact from, partially at least, from the web, because people can put into websites semantic annotations, and you find then here some of these semantic annotations, like when you search for Men in Black, this famous movie, director was Barry Sonnenfeld, and here there was a rating that is displayed on the Internet Movie Database website. And so this is information which is not just in running text, but which has been provided as metadata in the background for Google to collect and build a large knowledge graph. Again, when Google collects this information, the question is whether these are only true facts or false facts. So a friend of mine worked at Yahoo until a few years ago. They also used this metadata for their search. And he said, yes, there's also a lot of spam, a lot of false facts on this metadata. And they weren't allowed to tell which kind of false facts, because it was an arms race between the search engine providers. and the spammers in producing and deleting these kind of false facts. So what does Google use the knowledge graph for? Of course, for providing information about objects. For example, here that object was object information about Men in Black on the right. And directly you find not only that on a particular website, it says the director was Barry Sonnenfeld, but it says directly as factual knowledge who the directors were, what the production companies were, and so on and so forth. And of course, it shows some pictures, so you better understand whether that's what you're interested in. So Google uses this knowledge graph especially for typing information. It guides the natural language processing, it guides the machine learning, it guides the alignment of information. And they also have metadata types where they distinguish between what are entities that live in time. So humans live in time, are born and die, but other things, they are taking place in time. So when we consider the Glastonbury Festival, which just happened on the last weekend, I wasn't there, unfortunately, but then that started before the weekend and ended with the end of the weekend. And it is really constituted only in this weekend. And this is a different kind of thing, because now you can ask different questions. You can say, I want to participate in the Glastonbury Festival, or I want to participate in LDAC, which is another such event. So the questions you can ask are different when you have such information. It would be a bit strange to say, can I participate in Steffen? Yeah, as would be a really strange question. And of course, this typing and meta typing information allows you to sort out what is probably meant. I think to some extent, knowledge graphs in architecture are still at the beginning. Let me point to some other places, which I think are not so far away from with the challenges, but where the knowledge graphs have been around for a bit longer. One place, this here is a picture I stole from Evgeny Kalamov from Bosch. This is a picture which depicts their vision of using knowledge graphs in the manufacturing industry. So the idea is, or the general problem that you have in companies is you have tons of data. The problem is that all of these data are in information silos. And then people try to make sense of the data and integrate the data that they have from these different information silos. Very often what they do is that they construct a data warehouse or a data lake or data marsh, or however they call it. And the problem is that this only helps with regard to the first challenge, namely with having one platform to even be able to store the data on. Yeah, when you have data lakes, there's not really much of a combination between these different data lakes. And you have to do hard work in order to access and combine information from these data lakes. Part of this hard work, or most of this, or a lot of this hard work, doesn't go away by using knowledge graphs. Rather, the knowledge graphs is a vehicle to bring information from these data lakes together. And so you would use terminological knowledge in order to include different databases, let's say a relational database and a graph database. You would also use the factual knowledge. Let's say if you build a certain product, then you do not only have terminological knowledge about this product, but also factual knowledge about this product. You have a particular car, and the particular car comes with a particular engine, which has a particular number, horsepower, strength, and so on and so forth. So you can take such a car, a specific product, as a point of integration of information found in the different data lakes. Again, in this situation, identity is a huge problem, which is typically underestimated, at least when people see it for the first time. Then, once you have this integration of knowledge and facts, then you can come to insights. You can do all kind of analytics. You can try to look for patterns, you can explore the knowledge, you can apply machine learning, and then you have an AI stack that allows you to do interesting stuff, from natural language processing to business reporting, to rule learning about what are the patterns in this knowledge graph. And once you have these insights, then you can apply them in order to create actual value for your actual industrial processes, whether that's procurement, simulation, manufacturing, and so on and so forth. Because with these industrial processes, you can then try to optimize and see, is there something that creates all of the cost? Think about how can I get rid of this particular process step if that's so costly, and things like that. So this is a generic use in the industry. One, I think, that also applies in the field of architecture and construction, because when we have all the knowledge integrated together, we can investigate what are our pain points, what makes our buildings expensive. Can we somehow do away with one of the steps, or can we replace something by a cheaper counterpart without harming our overall building? Okay, let me jump over that. These kind of things are not just theory. So in some industries, for example, in the Norwegian oil industry, they started projects about this like 10 years ago. They had this problem that they had information about the ground, and so the ground in the North Sea, and about the oil fields below that. And the problem that they had was that they had a huge amount of information, many terabytes of data collected in thousands of tables and tenfold the number of columns. And now when they wanted to get to information, they basically had to ask someone to put together a query. And they measured how long that would take. So getting to data they had in this data store already took 4 days. Why did it take so long? Well, first, the people who wanted to have information, they didn't know how to write such a query. So they had to ask someone else. There's someone else maybe didn't know where exactly this piece of information was, and maybe only had a partial knowledge about the challenge that the people who had the business process were interested in. So this was a very expensive process of asking the question, getting an expert to be able to pull the queries together from many of these many tables. And thus this data gathering for working on your process was a large bottleneck. So with having the knowledge graph around, the knowledge graph tends to be easier to navigate for, let's say, not an IT expert, but a domain expert, because it captures in a rather intuitive fashion what the problem is about. And of course, it offers all these hooks, terminological hooks and identity hooks to drill into your data, provided that, of course, the data is already correctly connected, and then allows to formulate questions at a much faster pace and a much more intuitive level. This example also illustrates why it's sometimes quite hard to show the return on investment for knowledge graphs immediately. The problem is that having more intuitive access to such data is often hard to measure, but it is clear that when people can query for the hidden knowledge and they can use this knowledge, that this is a very valuable source. And if it takes 4 days, you think 10 times, not just twice, but 10 times before you ask someone this question to do it for you. And maybe 4 days later, you might have forgotten even why you asked the question in the first place. Here's another example, knowledge graph for product design at a manufacturing company. And again, the problem is about connecting the offers that these manufacturing companies, they provide, for example, different kind of engines, linear engines, and here are some motors, controllers, and build them into complex products. And when they want to make an offer to a client, and this requires the development of such a new product, of course, they don't develop everything from scratch. They don't develop then a new motor or a new controller. They rather look into what do they have around, how can they adapt it? And they need information about what fits together with what else. And so what you need is data about all these different components, and you need to be able to link these different components together. Again, this may be, it's just much easier in a knowledge graph than if it's all hidden in such relational tables. Obviously, you have described these different products in tables already. So you don't want to throw away this information. It's also in well-running, established information systems. So a major problem is, of course, to lift that information into a knowledge graph solution, which allows you then intuitive access to combining these components into a product offer. Okay, so that brings me to this summary on industrial knowledge graph. So it was quite a bit slower than I expected. And here is some summary for the paper that we show here. I will share the slides, so I don't think I have to read it here. What are pervasive challenges when you build such large knowledge graphs is, first, there is a huge modeling challenge. There is not one way to build the right knowledge graph for your task. So this is, this is a big problem, because people ask me for what is the right way to do it. And I say, you can do it this way or that way. And with this way, the one thing is easier, and with the other way, the other thing is easier. So the Elsa smiles because that's, I think, the answer I've given to her many times already. That's the one thing. The second thing, graphs get large, because if you capture a lot of information, you just lose the oversight. Yeah, Jamie Taylor, oversees the Google Knowledge Graph team, says, these graphs are bigger than my brain. I have a funny example to report from during my PhD studies. My PhD advisor and the medical doctor, they investigated the UMLS anatomy. And the UMLS anatomy developed by the National Institute of Health. Now it has like 1 million concept. That certainly wasn't as big as that, like this many years ago, but it was big already. And they found that the human left breast was modeled differently than the human right breast. And there was no anatomical reason for it. It was just that the way these two parts of the breast were modeled were somewhat incomparable. And the reason is just that when people model in different parts, it's very hard to oversee for them how do other people work and model in other places. So for Google, it seems to be, at least rumor has it, that it's 600 people. That's, of course, for a very large company where information is so core. Machine learning and data mining is core in several ways. First, for creating the knowledge graph, for refining the graph, having more instances, for completing the graph. It is very difficult to have tens of millions of instances just by manual addition, because this is only possible with 10,000s of editors. And even then it's a challenge. So you have to think about how to move data that you have into such a knowledge graph to refine it, maybe do some learning, maybe include some natural language information from text. Identity and entity alignment is a huge problem. It's different in the different industries. I know, for example, Zalando, this fashion platform, they have a big problem about what is the same skirt or pair of trousers. They even use vision mechanisms in order to establish that two skirts are the same or are different. The problem is, of course, that the metadata that the providers of these fashions provide are often not complete, and or they are very unstructured and very hard to analyze. And so knowing that two skirts or two pairs of trousers are the same or are different is a challenge here. So this, of course, has to do with the different sources where your data comes from. The different sources can be within your company, like the example with the oil industry, 3,000 tables. It can be different providers that deliver fashion to you, or that deliver electrical gadgets to you. You always have different sources that have different qualities of information. And even if they have high quality, they have different schemata of how they provide the information. That also means you have to track the provenance. Where does it come from? To also find out, can I trust this information if it comes from this or that provider? Of course, it could easily be that if something is just lost in the information space, you have a contractor, and the contractor provides just rubbish information. As long as no one complains, because no one can tell where that rubbish information came from, they might just proceed like this because it's cheap for them to do so. So now I could talk like another hour or so about semantic technologies for infrastructure, but I think that would take too long. So I'd rather take some questions, discussions, comments now, and only if we have a lot of time, I would go into a bit of the semantic technologies.
Someone needs to mute. I don't know where is this coming from. Okay, we can continue. Sorry.
Any questions, comments?
I have a question. So you told us that knowledge graph can be used to integrate data from different sources because it provides a model that is simpler than just putting in a same database all the tables or thousands of tables. And that was something that was, for instance, I know that Juan Sequeira used these translations, integration using transformation from databases to graphs, and in the particular case to RDF. So my question is, now we are also seeing a rise of property graphs. What is your vision between these two models, property graph and RDF model? What are the advantages and disadvantages of these two models?
Okay, then let's look into the two models. So I don't have a slide now for property graphs, but I think I can explain it with the core RDF data model. The core RDF data model is simply that you talk about triples. So here, for example, the RDF semantics document was edited by Pat Hayes. So RDF semantics document is the subject, edited by is the predicate or relationship, and the object or target of this relationship is Pat Hayes. And this is even a bit simplifying because I just write the names, RDF semantics and Pat Hayes instead of proper identifiers where the identifiers have names, because obviously if you look around, there will be several Pat Hayes in the world, even though the one who edited is really a unique and very clever figure. So, but just if you look for this string Pat Hayes, you will find many, of course. Okay, so this is the model. Now, this model has shortcomings because it doesn't say when it was edited. And especially when we think in terms of RDF, we have different versions. We had RDF 1.0, RDF 1.1. In the future, we may have RDF 2.0. So it is actually not good enough just to know that this document was edited by Pat Hayes. He may have edited it once or twice, and we don't have this kind of information. So in RDF, we would not now have to construct an extra node and redo our model. Now, what I said before is very important, is that the important thing about knowledge graphs is that they must be easy to deal with. Now, when we now remodel this model and we break up this relationship between RDF semantics and Patase in order to construct a new node, which is the editing node. And with this editing node, we attach like when it was edited. We make our model more complex and we lose intuitiveness. And the problem then is that with this loss of intuitiveness, we lose customers who are not interested in this additional information. And the big challenge is to cater to different kind of communities, to different kind of customers, users of our model at the same time. We need to cater to those people who are only interested in this very simple relationship. RDF semantics was edited by Patase. And we, at the same time, we need to cater to those users who are interested in knowing exactly when Patase did that, or even which tool he used for editing that document. And keeping intuition while providing expressiveness, this is a permanent challenge. Of course, that's often in logical representations, also in databases. This is a continuous challenge that we have to face. And I think, of course, Daniel, you know the more recent developments like RDF star and likewise things. I don't think we have converged yet, but I think we're approaching a point where at least this gets easier to do and it can better be done to preserve the easy capabilities for easy tasks while still allowing for the challenging tasks.
Thank you. So it seems that RDF star is already similar with a property graphs. And I also,
I mean, there are some details where it's different, yeah. But yeah, maybe that would require more detailed look and a more detailed comparison that we can do now.
The current workflow, what we have right now at the workshop, we are converting everything to RDF. But let's see in future what RDF star can bring on the table. I find the cross-platform data querying in graphs very inspiring. The way we can discover knowledge is definitely what is needed in the building industry, because all information is split in disciplines and also fragmented in different stakeholders. So semantic web can definitely solve a lot of problems about data interoperability. But I wanted to ask a question on the patterns. What exactly is finding patterns with rules using knowledge graphs and semantic reasoning? Could you elaborate a bit or give an example?
Yeah, let me try to invent an example from the top of my head. I mean, the examples that people have looked at academically, these are easy ones. For example, Fabian Suchanek has worked on AMI. People in Mannheim have worked on AnyWorld. And then they investigated Wikidata and they find that there are rules like if you're married and you live in a city, your spouse probably also lives in that city. Of course, that rule is not 100% correct, yeah? Obviously, there are spouses that live apart, but maybe it's correct in 80% of the cases.
Yeah.
And you could, of course, apply this kind of rules also to the architecture and construction domain. You could ask questions like, why does it happen that we have a certain, what is common in different projects that leads to a delay in certain fabrication, certain construction? Yeah, do they have some commonalities? And this is what you would try to find then. Is there some possible common cause? Of course, this is a difficult challenge because you might also find stuff that you already know. Yeah, you might find that, okay, larger buildings lead to more delays than smaller buildings. Yeah, that's what you would expect. Yeah? But there might, of course, be other reasons that might cause delays that are not so easily understandable.
Yeah, I can see it probably based on the material or based on the building system or based on some other detailing.
Yeah, absolutely.
Thank you. And do we have any other questions from the audience?
Well, by the way, one very funny idea for also these kind of queries and rules I learned from some engineering company who said that they would like to query for all the different parts, and they would know the weight of these parts and the cost for these parts in order to get an estimate which products are too expensive.
Oh.
Because oftentimes, I mean, of course, it will depend on what do you buy. Do you buy computer chips? Obviously, they will be rather expensive per grams of weight, yeah? But if you compare likewise things, like you compare screws, yeah, then probably you want to learn that, or you want to find the outliers. You still have to apply your human intelligence then to look at the outliers and say, okay, is it plausible that now this particular screw costs in a way too much concern with relative to weight compared to others? There could be a reason for it, a specific material, which is more expensive. But looking over thousands of components and trying to establish these tendencies and trying to find these outliers, even based on such simple correlations, because quite often these costs are based on history and not on a thorough competitor analysis. Yeah, so there it could well be that also in your construction, the costs are not quite optimized, but it's very hard to spot.
Yeah, I can see that. Fatima has a question. Yes, please.
So pattern is a likely reason, but it's not a fact.
Pardon me?
Pattern. So when we were discussing pattern, you said like something that is possibility for like 80%. So it's a likely reason, but it's not a fact. Like rules are for 100% thing.
Yes.
But patterns are for something maybe 70, 80%.
Yeah, I mean, the rules, what you do is you indicate the quality of the rules that you're interested in. And you typically measure the quality of the rules in terms of support and confidence. With support, you measure how often this rule applies. I mean, you might find a rule which is perfect, but which just runs a single time. Then it is hard to say that this is a pattern. So you want to have rules that apply at least often enough, right? And then you have confidence, and the confidence measures in how many of the cases that you run this mechanism, is this rule correct? Is it 70%, 80%, 90%? What is it? Yeah. And of course, when you find such rules, you might not want to automate them, but rather, well, there could be several reasons. Quite often, you're interested in understanding the rules and learning, and then changing your process because of the rules. That could be an outcome. You could discover that your data is incomplete. That's what people do, that they say, okay, there should be the rule. Now, for example, if I know about Daniel and where he lives, and then if I don't know anything else, I assume his wife also lives in the same place. Yeah, and maybe that saying that unless I know otherwise, this also boosts your the applicability of the rules. Yeah. So that's where, of course, people explore different kind of strategies in order to boost the usage of such kind of rules.
Okay, thanks.
Welcome. Navid?
Yeah, thank you for that talk. I just wanted to ask you, when it comes to designing ontologies, can you give some practical tips about some of the big pitfalls, like, I don't know, maybe choosing the wrong OWL reasoner profile, or inferences that are, derived that shouldn't be there, or something like that?
I mean, what you want to start with are requirements collection, like competency questions. And there the question is, what do you want to accomplish with your ontology? The ontology is in one or the other way abstract and doesn't rely on a specific reason. I mean, you can always change the reasoner one for the other. the OWL reasoners are rarely used directly in knowledge graphs for on-the-fly question answering, because that's typically too slow. So what happens is that you may use an OWL reasoner to build your ontology, but then you materialize the structures, and then you can materialize these structures in RDFS taxonomies. And that will be rather scalable. There are also other approaches which use the ontology for query expansion in a certain way, like ODBA mechanisms. I think that few people rely on OWL ontologies at runtime. There are a few examples like the SNOMED ontology that use very simple profiles, OWL-EL, but I don't know of any large ontology that would use a very expressive OWL profile. That's what more and more people use also to model ontologies is Shackle. So most people, or many people, find it easier to think in terms of, I think the Shackle syntax is quite convoluted. I'm not a big fan of its syntax, but people find it rather natural to think in terms of Shackle because it's the way you think about a database. You think in terms of, if I have an object of this type, this attribute should be there. And that's something that people can understand very well, whereas in OWL, you have this open world, and then if it's not there, okay, you postulate it will exist. And people have a hard time with that. And because of that, they make modeling mistakes. I've also seen projects by friends done where people misused OWL, and then the friends translated the wrong OWL model into a closed world interpretation. So the question here really is, who are involved in your modeling process? What is their understanding? What are your requirements? What do you really need? Do you really need OWL-EL? Maybe. Maybe you would be happy with less, or you use OWL only for the construction part of the ontology, and then you basically extract the stable ontology from it. There are many possible ways. It also has to do with, I would say, with the people you have. Yeah. So a friend of mine who had worked for Microsoft before explained it like this. They say like the Microsoft programming environments are not made really for the top-notch software developers, because they don't allow really for complex meta modeling and meta programming, what some of the most sophisticated programmers might want to do to be very effective. The Microsoft programming environments are rather made for the average programmer and the incoming developer, because that's the large mass of people. And therefore, they don't offer some of the most sophisticated stuff, because that might be something that people can, or the majority of people cannot deal with. So you need to also choose your tools in a way that your developers are happy with, can work with, and not the other way around, sort of like you choose your tools only based on objective criteria which don't exist. These criteria are not really objective. They always have to do with people.
Thank you so much. Thank you.
You're welcome.
Irfan has a question. Yes, please.
Yeah. Thank you for this presentation. I was wondering, you showed some of these examples, industry examples, and they focused mostly on these large-scale global enterprises. And in construction, I think, as you mentioned, there's more this fragmentation. I was wondering, do you have any insights on knowledge graphs for these kind of companies, like small, medium enterprises? what are
I think the difference is not that large, because these big companies, they also consist of departments that hate to talk to each other. Yeah, so I know the previous chief information officer from Deutsche Bank, the largest bank in Germany and internationally active. And he said his sole job was to go around from department to department and convince people that they release their data. So, which is not much different than having different companies that need to exchange data. Of course, there are some things that make it easier. So when I go to university, we have a single sign-on possibility. That's something what you typically have within a large corporation. So this kind of elementary technicality is then already solved for you. But anything much deeper than that is also a problem in large corporations. You may have more things, maybe in some company you have, but even the platforms, like what someone from pharmaceuticals told me, the problem is that they have these centralized databases, and when they need a new column to represent something, they can ask the central administration, and then it takes 6 months until they get the new column. But they cannot stop working for 6 months. So what do? They create their own local database and work with that. And because of that, they also have thousands of databases in the pharmaceutical companies, which is even a big mess for them, because once you release a drug, you need to show that you did all the proper care all along the way. And in a way, you then need to have this track record of how the data move through the different databases, which is difficult when you have 1,000 databases. So basically, in these large corporations, also people don't know where their data ends up and how it's used. And when you are on a big social media platform, you have private data there, and you then say, delete my data. And yeah, it's deleted in one place, but there are probably 10 other places where your private data still lies around, simply because the platform provider does not know where your data actually went after it was once stored in some interface. Yeah. So this is a bit comparable to the distributed setting.
Okay, but do you think there is somebody in the construction industry who could foster this? Should it be like Autodesk to say, okay, we implement this, or?
This is a good question, but it's a strategic question that goes beyond my strategic knowledge of the AAC environment. Okay. Yeah, and I mean, one could of course think, I guess some association would have to do that, right? Okay. It's probably hard to see that a single company could impose that. And probably if a company creates something, then there would be the question, why would other people take this up? I mean, Siemens, I've had some chat with Siemens in this area of monitoring buildings and controlling buildings. And there Siemens wants to provide the cloud services, and they provide the ontologies and the tools for ontologies for free, because they want to make the money only with the cloud services. And they want that other people make money from selling products, gadgets, consulting, and so on. They don't want to do that because they say it's not enough money for them. They only want to have the cloud services. So then of course, maybe that could be a reason, a bit like Amazon Web Services, where Amazon provided the platform, and then other people just jumped on board because there was a large player to then also emulate that. So there was an open source version of the Amazon Web Service environment. I don't remember now what this open source counterpart of S3 and so on was, but it was basically the same infrastructure, just because there was this big player. That might perhaps be a way, but I don't know. This is
okay.
Complicated politics.
Yeah, thanks for this.
You can lower your hand, Irfan, if you want, because then it's confusing. Thank you. Do we have any other question? I guess there is no question.
Okay, then I say thank you again for inviting me to give this talk here today. And I hope that you still have a great workshop.
Yep.
I'm sure you'll do.
Thanks a lot, Professor Staab, for giving us time, for taking the time to give this talk. And then we continue the workshop with Daniel giving a tutorial on GraphDB. Okay,
Thank you.
Professor Staab.
Thank you, Professor Staab.
Yep.
Thank you. Have fun.
Thank you.
Cheers.
Now we continue
Bye-bye.
with our building information modeling with knowledge graphs. We already have actually right now I see that there are some people that are still not part of the workshop, but if you want to continue exploring GraphDB, you can stay, then later we will start working on the groups. So the people who are registered for the workshop can continue, but who wants to follow the tutorial that Daniel will walk through can still stay. Daniel, then I introduce you again. Daniel is Professor Staab's postdoc. Maybe you can introduce yourself and the floor is yours.
Yeah, so I am a postdoc in the University